So we're saying a likelihood measure is referred to as the probability measure. It measures the probability of an event. It measures the probability of an event. So that's important. So here you have your sample space, which includes all possible outcomes. Then your sigma algebra, which is a collection of all events. And then your probability measure. And so on. Now, we have a probability, the probability of an event A1 occurring. So you could just write it as probability that A1 occurred. Actually, you can just use P, doesn't matter. Then, if the probability of the union of A1 and A2, so if you take A1 and A2 combined together, then you have the probability of A1 union A2, as you can see there. And then we have the probability of the intersection. That is quite interesting because now the probability of the intersection between A1 intersection B, that one sometimes can just be written as probability of A1 B. And we're going to really look at this in our bias principle. Now, when you're not assuming disjoint set, then you have something that we call the inclusion-exclusion principle, which means if I take the probability of A1 union AB, it's just going to be equal to the probability of A1 plus probability of B minus probability of A1 intersection B. I don't know. Are you guys feeling more, or is it just me? There's only one family in this class. We will survive. Are you getting this one? So what I mean, I'll take the probability of A1, then take the probability of B, then subtract this intersection. So that's called the inclusion-exclusion principle. So when the two sets are not disjoint, which means they have a boundary and they're not cutting into each other, that's what it will be. So inclusion-exclusion principle. What you're saying is I have the probability of A1 union A2 union B is just going to be probability of A1 plus probability of A2 plus probability of B minus the probability of the intersection between A1 and B. Okay? Then, if they are now disjoint and cover the event space, if they are disjoint and cover the event space, what we mean is that A1 and A2 are disjoint and cover the event space. So we have an event space like this one. Then you have A1 and A2. Their union is just going to be, the probability of their union is just going to be 1 because it covers the entire event space. So if I take A1 union A2, we say this is just going to be 1 because it's the entire event space. Now if you look at the intersection, they're not intersecting anywhere because they're disjoint. So A1 intersection A2, their probability will be 0. They're not intersecting anywhere. Is that fine? Now let's go to the good old bias theory. Very religious man, this bias guy. Was trying to figure out on existence and presence. Wait, you copy all the slides? Like everything on this? Oh, okay. Oh, yeah, because you have these things on your classroom. Yeah, so you can read about bias story. It's a funny one. So we want to look at conditional probability and independence. And here, how we start that is on conditional probability and independence. And I think it will only be fair for us to start from Bayes' theorem. Yeah, I was looking for this example. Okay, so we've talked about a probability measure. Okay, we've talked about a probability measure, which is a triple. So the probability measure, now we want to define this probability measure conditioned on another probability measure. So we want to look at the probability of an event A occurring given that B occurs. So for instance, we say the probability that Michelle will come to class given that I've insisted everybody should be here by 8:30. Next time it's 8:25, guys. Kujeni tu mapema. Yeah, so those are conditional probability. The probability that the students will miss exam given that they've not revised and come up with an interesting reason to do a special exam and so on. So conditional probability is just a probability measure that is defined relative to another probability measure, and this is called a conditional probability. So for conditional probability, it's still going to be on that event space. So we can say probability measure describe relative to another probability measure. That's what we call conditional probability. Conditional probability. Now, I don't want to get much into the theory, but I'll write it down for those who will be interested in understanding the theory. But in this case, we're going to define it in a unique way. So what you see there that we are stating as Bayes' theorem, so actually we could define this one. So let's again assume you have your event space, your probability space, which is a triple. Assume this is your probability space. And B is an event in A with probability of B not equal to 0. So probability of B is not equal to 0. So how can we describe the conditional probability? So we can calculate the probability that an event A occurs given that B has occurred. And this one, we are going to define it. We're going to define it by probability of A intersection B over probability of B. So that's the definition. So we are saying the probability that an event A occurs given that B has occurred is going to be the probability of A intersection B times probability of B. So A intersection B, you can also just write A comma B, and this is called the probability is that's called the conditional probability of A under B. The conditional probability of A under B. And I don't want to get to the abstract scenarios of this. The abstract scenarios. Okay. Now, I'm curious to see if you guys can answer this question. So, what does this mean? So that means, so what's the conditional probability of B given that B has occurred? What would be the answer? I don't overthink. So remember, that condition that B is not equal to 0 is important because we don't want to be dividing by 0. But, hey, Imashina, what's the probability that Trevor is called Trevor? One. So the Trevor is named Trevor, given that he was Trevor. It's just Trevor. It's just one. Yeah. It's just a probability that it's like asking what is the probability that that a student has come to class, given that a student has come to class. The student is already in class. So this student has come to class, so it's 1. Yeah? Yeah. Yeah. You guys don't want to go into investment banking and make salaries, crazy salaries. That's where engineers go anyway. Most of the people in investment banking, engineers and physicists and scientists, because engineering doesn't pay a lot of money, especially those who want a lot of money. And in investment banking, these are the questions that they will ask you. Actually, they're going to ask you, someone could ask you this question. So I just want you to take note also that in the event, so for the case where probability of B is equals to 0, then let's always just set probability of A given B to be 0. So define it like that, so that you don't get into those scenarios of dividing by 0. Now, I want to give an example before I explain what bias theorem is. So let's look at an model, and we are going to think about it being ordered without replacement. So can be a mafunzo ya probability and statistics. We wouldn't have been going through all these things. Tony, what were you doing with probability in the unit?
You know, that's like 3 years ago.
It's still soon. I learned mine like 12 years ago.
But you know, you are continuously teaching.
I've actually, this is the second time I'm teaching. Okay, so the UN model. So you know what an UN is? Okay? So we have, let's assume we have blue and red balls, or black and white. So let's assume you have that type of setup. Actually, let's make them 4. So that's an UN model. So what you're doing, you're going to pick a ball inside and then not without replacement, yeah? We're going to pick a ball inside without replacement. So our UN consists of what? Let me just say black and white balls, yeah? Black and white balls. Black and white balls. So I just want us to pick a ball from this UN at random twice, yeah? And we don't replace it. So we put our hand inside, then after it's shaken, just pick a ball. Okay, so we're doing it twice. So that means what's going to be your sample space? So we're just picking twice, a ball twice from the jar. What's going to be your sample space?
Two blocks.
You're assuming you'll pick two blacks when you pick twice. What if the first time you put your hand inside? Because you're not looking at the balls inside, just putting it and picking a ball at random. Okay, so the probability space is going to be actually, we're doing this experiment twice. So when you put your hand, you could pick a black or white. When you put your hand again, the second time you could pick a black or white. And you know it's without replacement, so you don't return a ball that you've picked. So it will just be this one times this one. So that's our probability space. So this just means we are doing this experiment twice. Yeah. So I pick the first time, I pick the second time, those are the chances. And this is a discrete probability space. Now, you could use the method we used in high school. Remember, I could start, yeah? I could start and then put my hand inside. So we have three, so I'll have 3 black balls and 1 white ball. So if I did my first pick, I could pick what? A blue or a white ball. What's the probability of picking a blue ball a black ball in the first chance? Yeah. Yes, Michelle? So we have 3 black balls and 1 white ball. So if I put my hand inside, what's the probability that I'll pick a black ball? Just say what came in your mind, whether it's correct or not. So you have 4 balls, 3 are black, 1 is white. You put your hand inside at random. What's the probability that you'll pick a black ball? A quarter. No, it's the opposite now, yeah? Because the black are 3, so you could pick one of the 3. So the probability of picking a black is actually 3/4. The probability of picking a white one is 1/4. That's the first pick, but you don't replace. So after doing the first pick, you only remain with 3 balls inside. So if the first one was black, and I go pick again, could have a black or a white ball. Yeah? So if the first pick was black, and I pick again, what's going to be the probability that I pick a black ball? So I already picked a black. So that means we are remaining with 2 black balls and 1 white ball. So the probability of picking a black ball is going to be 2/3, and white ball is going to be 1/3. But in this scenario, if I pick a white ball for the first time, then I go back, do this experiment, and have a black and a white ball. So I've already picked a white ball, so there's no more white ball. You're only remaining with 3 black balls. So the probability of picking a black ball is just going to be 1, because only black balls are inside. And then the probability of picking a white ball is going to be 0, because you've already picked it. You've already picked it. Yeah? So you can calculate conditional probability here. You can calculate the conditional probability such that, so actually, there are many probabilities you could calculate here. So I'm just going to resort to just using P. So the probability that you get a black ball and a black ball for the 2 picks is going to be what? It's just going to be 3/4 times 2/3, yeah? So that's which is 1/2. Then there's a probability that you could pick a black ball and a white ball the second time. That is 3/4 times 1/3. And that is 1/4. Then there's a probability that you could pick a white ball and a blue ball. That's white ball is 1/4, and a black ball is 1. So that just gives me 1/4. Then the probability that I could pick a white ball and then a white ball is just going to be a white ball is 1/4. Then another white ball, the second time there's only one white ball, so it will be 0, and this is going to be 0. That's going to be 0. Okay? So if I ask you the question, so the conditional probability I want you to calculate here is based on this event, and I'm going to describe this event B. So the event B, I'm going to describe it as the first ball is black. Okay? The event that the first ball is black. So the only scenario where, this thing locked itself again. The only scenario where the first event is, first ball is black, there are only two. This one and this one. So those are the only two events. So this will be event black, black, and event black, white. Those are the only two events where the first ball is black. So if you're calculating this probability, you just take because this is the union of these events, you could just take, that means the probability that the first ball is black is just going to be black was a half, then black white was a quarter, and this gives us what? 3/4. So that's the probability that the first ball is black. Now, you know, in theory, we are not even supposed to do some example. So just supposed to assume everybody remembers probability from back then. The probability, so I want now to calculate the probability that we have this event BW, given that B has occurred. Given that B has occurred. Okay? So how do you calculate that event? So the probability that we have the first peak being black and the second peak being white, given that B has occurred. So here we are going to do something. So we are going to take it as the probability of this first event, B white, intersection B over probability of B. Now what's the intersection of B white and B? That's a tough one and easy at the same time, because it's so easy to see. What is that event? What's the intersection? Can you just try to calculate it? You can see it even without calculating it. So what I mean here, so the intersection, this one, for the intersection, you're taking what? You're taking B white, and then you're intersecting with B, and B has two things. B has BB, and B white. So remember, the intersection is a common area. So if you're looking at those two circles, this would be your intersection, yeah? That would be your intersection. So we are trying to look at the common region between the two of them. It's just B white, BW. BW is in the both sets, so that means that's this common region. Because this one has just BW on this side, this one has BB and BW. So BW is going to be the intersection between both of them. So this can easily be written as BW over probability of B. And probability of BW, BW we have it here, is a quarter. Probability of B is what? Where is it? 3 over 4. So a quarter divided by 3 over 4, what is the answer? That is 1 over 3. That is 1 over 3. Yeah? Did you see that? So the most important thing is to remember the intersection. So you don't just assume it's actually something you can see. So you take this set as only BW, this set as BB and BW. BW is in both, so that's the intersection, the common region. So let's look at Bayes' theorem and the law of total probability. Any question? Bayes' theorem. So still under conditional probability and independence, Bayes' theorem and law of total probability. So for Bayes' theorem, that's or Bayes' theorem, depends on where you learn these things. So Bayes' theorem states that if the probability that an event A occurs given that B has occurred is just going to be probability of A intersection B over probability of B. And this one, probability of A intersection B actually is, now I want you to take note of something before, where does this one come from? Because it just doesn't appear from life. So take note of this one and look at this sum. So probability of A intersection B can be given as, so let me give another one, another example here. So I'll write that one here. So let's think of B given A. Actually, before that, let's write probability of A intersection B is equals to, probability of B given A would just be, again, probability of A intersection B over probability of A. So this one means probability of A intersection B can be given by probability of B given A times probability of A. So we could substitute this one here and have probability of B given A times probability of A over probability of B. So that's Bayes' theorem. That's Bayes' theorem. Now also from this theorem, if you looked carefully, you looked carefully, this one also here could be written as what? Probability of A intersection B is equals to probability of A given B times probability of B. What does that imply? It implies that probability of A given B times probability of B, which is just probability of A intersection B, is the same as this one here. So it's equals to probability of B given A times probability of A. So those two are the same. That's conditional probability. Okay, then so the next thing here we introduce is the law of total probability, and I think that will form our last part in these slides, and then we'll finish up the rest. So the reason why I've spent a bit of time here is for you to kind of start visualizing these probabilities. It's a very cool thing. The thing about probability, when you're learning it, it always seems very difficult. When you start knowing it, you wonder how was your life without probability before. It's way better than eating candy or cake or banana bread or all those things people do that make them die when they're less than 90 years. Can I clear this? No. Now, the next thing here is to talk about this law of total probability. Because and we will apply law of total probability when we'll be doing quantization, because we want to get optimal results. So you'll see how this becomes useful to us actually in our next chapter after the next. So it's the third chapter, quantization. So here, the law of total probability is very straightforward. So I'm going again to assume a probability space. Okay? Let me just use P without the thing, but just know that thing is there. So I'm going to assume this is my probability space. So I want to sketch here a rectangle inside this rectangle. I'll have a circle called A, and I'm gonna shade it. Yeah, so that's a circle called A. But then I'll split this again into two events. I'll call this B, and of course this one will be B complement, yeah? And this is my entire sample space. So assume that's a sample space, that rectangle, and we are looking at those events, yeah? So let's just say that A is an event, B is also an event, and you can see this thing has been split into two by B and B complement, so those ones just make up the entire sample space. B and B complement, their union, make up the entire sample space, because these ones are disjoint unions. Those are disjoint unions. Now, if you look at this half here, if you look at that half, this is A intersection B, this up half, because this region is both in A and in B, yeah? And then if you look at this other half, this is just A intersection B complement, yeah? Those make sense. A intersection B and A intersection B complement. Now we want to look at for something. So we want to calculate the probability of A. We don't know that. We want to calculate the probability of A. So how are you going to get the probability of A? So if you look at this one, probability of A will of course be this region here, union this region, because the two regions are disjoint, okay? It's just going to be the probability of this region plus the probability of that region. So that would be the probability of A intersection B union probability of A intersection B complement. Yeah? And please, when you leave this class after today, go and review through these things and try to comprehend them so that you don't memorize formulas. So this one, because I'm taking the union of this and this event, and we've said that one is A intersection B complement here, and this is A intersection B. So that gives me probability of A intersection B, because there is a union, and we say their additivity property, so we just add plus A intersection B complement. A intersection B complement. Now from bias theorem, remember we say that probability of A intersection B is just equals to probability of A given B times probability of B. So we can apply that here. So this first one will just be, that's from bias theorem, this one will just become probability of A given B times probability of B plus probability of A given B complement times probability of B complement. That comes from bias theory. So the second step is, because of disjoint, because they're disjoint, you apply additivity. This one comes from bias theorem. So remember, our bias theorem was just P of A given B is equals to P of A intersection B over P of B. So you can use comma or the intersection sign. Now, so that's what we call the law of total probability. The law of total probability. Now, what happens if we have countably many sets? So here we are looking at a case where it's just been divided into two. So what if you divide this set into many sets? So we have the case for countably many sets. The case for countably many sets. So here, so what we mean here is, so we are still on law of total probability. It means that you have the i's that are now events in A for, okay, I think I'm just going to write this, but so I is an index set, which means I is just from 1, 2, 3, 4, 5, 6, 7 up to infinity. Yeah, and they're integers. The index set are natural numbers, not integers. So this is just natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to infinity. And then, so with the same thing, we say that the union class one or watch movie. So the union of all this is going to be the sample space, and these ones again are disjoint events. Now I'm gonna sketch, because I know some people, when you write the mathematical language, wanapotea kidogo. So the union of this, all these events bi. So instead of just having two b's, we are going to split them into many of them, like 100, 1,000 of them. So we are doing the same thing, but now with many b's. So let's just visualize this. So what I mean is, so you have this is a sample space, omega, and then we have is the b's, sorry, 1, 2, 3, 4, many of them. It's going up to like infinity. So here you have B1, B2, B3, B4, and that keeps going, okay? So that's what I mean. So this is how we've divided our sample space into this countably many countably many sets. Then our A is still there. Let me assume A catches all of them. So that's my A. That's my A. So we are doing the same thing with that being A. So I want to write the, what do you think your theorem now will look like? The total law of total probability. Now, law of total probability is just probably one of the most important tools that you're going to learn. So here, again, I'll find the probability of A. And the probability of A, I'm just going to take, remember, we took A intersection B and A intersection B complement. We did take those two. So the probability of A is going to just be the probability of A intersection all those B's. So you take each intersection. Then after doing that, so A intersection BI, then you combine all of them. Because they are disjoint, you can use the union. I in the index set, then you combine them. So it's just taking A intersection B1, union A intersection B2, union A intersection B3, union A intersection B4. That's what we mean here. A intersection B1, A intersection B2, A intersection B3, A intersection B4. Now, these are disjoint unions, so that means additivity can apply. So you can apply additivity and do the sum. So this index set means we are just doing it from I is equals to 1 up to the number we have, n or m, all those numbers. So we can just add them. So we can take probability of A union BI. So that means I'll take probability of A union B1 plus probability of A union B2 plus probability of A union B3 until we are tired. And each of these actually can be given as I in the index set. And this one you can use bias theory. So here we've used additivity. Because these ones are disjoint unions. Now we can use bias theorem. And then what will the last expression be using bias theory? Yes? It's still on the board, guys. Maybe write it the so the last expression after that. Just use bias theory. So we're spending lots and lots of time here because we'll use this knowledge a lot to cover most of the other chapters. Yeah, I really hope from the next ones we now go faster. And I hope you guys are readers, so you can read most of the things. Have you written? Then I'll leave you with a Monty Hall problem that you're not supposed to calculate. Just think about it. Then when you meet at 11:15, mniambie. You know Monty Hall problem? You actually just substitute. That's the formula is there. Only you use bias theory. So what you're substituting is that theory. So in engineering, they can allow a quorum of 3 for selection. So let's say like everybody drops and you remain 3 telecoms. Does that unit go on? No? Or you don't know? Because that would really be nice. You could just have a lesson where we sit down on the table and just work it on a piece of paper. That's how they teach it also. The lecturer and the student will just sit on pen and paper. So you get to do more of the work. Yeah, so we just substitute the same thing. So this is the formula here. We use bias theory. So that becomes probability of A given BI has occurred. That's a condition of probability times probability of BI. So this is what we call the total law of probability. This is what we call the law of total probability. The law of total probability. Now, I want to leave you with a problem. It's called the Monty Hall problem. So just write it down that you can think about. Do not ask ChatGPT, do not Google, just find the answer yourself. Now, the problem is here. So you don't need to write the problem itself. Just write the title of the problem, then it'll give you the solution. So we have 3 doors. So you have 3 doors, numbered 1, 2, 3. So you are allowed, so you have 3 doors. So one has a car behind it, one of the doors has a car behind it, which is a better price to win. So it's a gambling competition. Then another door has 2 goats. The other 2 doors have a goat and a goat, so 2 goats. So of course everybody would want to win a car when you are going out there to gamble. Yeah? So the game master or the show master allows you to pick a door. Okay? So you pick a first door. You pick a door. So you could pick door number 1. So the show master will now open another door, mostly a door with a goat. So you pick one door, which is not open after you pick. Then the show master will pick for you another door, which has a goat. So let's say you pick number 1, then the show master picks number 3. Number 3 has a goat. So the show masters ask you to make a final pick. Would you stay or switch? So you picked number 1 that the show master does not open. The show master opens number 3 that has a goat. So one of the doors that has a goat. Then they give you a final chance to have a final pick. Will you stay or switch? What will you do if you're a gambler? I don't want even to think that much.
First one you pick a door.
Yeah, so you pick door number 1. Then the show master will open for you number 3, which has a goat. Our goal here is to win the biggest prize, which is a car. I know if you're from Rongai, you'll probably be satisfied with a goat. But
He also picks any at random.
no, he doesn't pick at random. He knows which one has the goats, which one has the cars. So you pick the one that has what? You pick one, then he opens for you the one that has a goat. So they ask you, are you going to stay with one or are you going to switch to 2? So that's the question you need to answer me when you come back. And tell me the actual probability that your pick has the highest probability of getting the car. Okay? Of the 3 doors. Okay. So we'll just start from law of total probability. Let me just give you the sign thing. I'll ask Geraldine to